Hey everybody, this is Matt with mathsmath.com. Thanks for joining us here today as we talk about rational exponents. We are in the Common Core Standard of Expressions and Equations, and we're going to be using these properties of exponents to create expressions that are equal to each other and solve real-life problems today. Our guiding question is, how can we find a number with rational exponents? What is that number going to equal? In the past, we've looked at positive and negative exponents. Now we're going to do some rational numbers. You remember what a rational number is? Well, if you don't, that's going to be your first step. Rational number, if you remember, is a fraction. Any number that can be written as a ratio. Definitely look at the name here. Ratio is in the word rational. Also rat and ion, but those are inconsequential. So, yep, definitely ratio. Ratio. It's a fraction. Okay? All right, so example equation where we're going to be using rational exponents is something like this. The moon travels around the earth, correct? You guys all agree with that? I hope so. And the earth is in the middle of the orbit. Well, the moon travels around, and there's a particular equation that we're going to look at. You can see it right down here, of the speed that the moon travels around in orbit of the earth. And that has to do with rational exponents. So that's what we're going to be dealing with today. Pretty cool, huh? All right, so let's talk about it. It might be a little bit confusing, especially having a fraction up there. You might have no idea. Remember with negative exponents, it was pretty easy. We just put the number, if it's got a negative exponent, if it's in the numerator, we put it in the denominator. Just put it on bottom. Pretty easy. But with rational exponents, a little bit different. We have to talk about these two words, base and root. All right, base and root. Let's define these real quick. All right, with base, it's basically base the number with the exponent. So here, it's the 5 or the x. It is that number that's at the base of the exponent. Pretty simple, right? Now the root, a little different. It's like square root. You have heard that before. Well, it's the number that's raised to that exponent, and it gives the original number. So for example, this here is the root. We're taking the square root of 4, and we get 2. 2 is the square root of 4. Makes sense? 2 is the root of 4. That's the simple example. A little bit harder example, we're going to talk about the cube root. Well, 2 is the cube root of 8. And notice we put the radical here, radical with the 3 up top. Okay? And then the one that is just mind-blowing with a whole bunch of letters that you might have no clue what it means, well, here it is. It is the nth root of x is y. So we call it the nth because there's an n there. And the nth root of x is y. Give me a random number. You could have put a 3 there, 3 for n, put an 8 for x, and what spits out? You get a 2. Okay? This is just math language, and we talk about this in math land, and you'll be seeing this way more as you get further in math. Okay? All right. I want you to try and figure this out. I want you to solve for x. Here's the problem. You have the square root of 4 equals 4 to the what power? Solve for x. Can you do that? All right, you need a hint? Okay, let's try this. What could you do to the radical to get rid of this guy? What could you do to this to get rid of it? What do you think we're going to do? Any ideas? Let's try this. Why don't you try squaring both sides? To get rid of the square root, you square both sides. So here it is. Here's the square root. If we square it, it makes this go away. But if we square this side, if we do to the left, got to do it to the right, so we square this. What does this become over here? What happens next? Well, you get this. 4 to the first power. I put an invisible 1 here. They're invisible. Doesn't matter. Put a 1 there. It's all good. And what's left over here? Well, you take the 2 and multiply it by the x. Anytime you have something in parentheses and then you square it or put it to that power, you take the 2 and multiply it by the x. Might not know that. So we get 4 to the first power equals 4 to the 2x. Well, what can we do now? Try this. What does x equal then? Well, we know that 4 to the first power was 4 to the 2x power. So 1 has to equal 2x. So what does x equal? X equals 1/2. Pretty basic, right? So when you think about it, the basic rule is that when you take the square root of x, it equals x to the 1/2 power. Pretty simple. Okay? All right. Why don't you try to do these ones on your own? What would you do with this one? The cube root of x. What would you put up with that question mark right there? Need a hint? Here you go. Well, if you think about it, remember the invisible one that just can sit right there? You put the 1 up there, and you take that 3, and you put it in the denominator. That's going to be our pattern from here on out. That's the big hint. All right, what are you going to do with this one? It's pretty challenging. The cube root of x squared. What fraction would you put there? Any idea? Take a guess. All right, try this one. Here we go. Well, if we see that the cube root of x to the first power is 1 over 3, take the 1, put it there, 3 there. The cube root of x squared is x to the 2/3 power. Not too bad, huh? All right, so what we're going to talk about now is defining what a rational exponent is. And this is how we do it. The numerator of the exponent is the actual exponent. So look here. That's the numerator of the fraction. And the denominator is that number right there. Okay? Example, like this. Uh-oh, a whole bunch of letters. Don't be scared. The a is just that number that we're going to put there. That's in the numerator of the exponent of the fraction here. And the b of the radical here goes on the bottom. Okay? That's your basic rule. Write that down. You're going to need to know this. You're going to see it all the time in this lesson. All right, so I want you to take these guys and try and solve them. Evaluate and simplify them, would you? Look at the first one here. What number times itself 3 times is 27? Now, it's not 3 times a number. It's what is a number times itself, times itself, times itself to give you 27. Any idea? Well, ironically, it's 3. If you think about it, 3 times 3 times 3, 3 times 3 times 3 is, that's 9, and that's 27. Bam. That's what you got. Okay? Let's do this next one. The 5th root of x to the 10th. Remember how you do that? Is this go on top or on bottom? Top or bottom? Okay, well, it's going to be x with top or bottom. 5 goes on the bottom. 10 goes on the top. And just like any other fraction, you're going to want to simplify. So this becomes x squared. And that's it. Not too bad, huh? All right, let's try this one. 16 to the 3/4 power. What are we going to do? Well, let's write it with our little exponents here. Put the radical, put the 16 inside. Now, remember where the 4 goes? 4 goes on the outside. 3. Bam. Okay? But what we can do is we can take the 4th root of 16 and do that first. Well, the 4th root of 16 is the sum number times the same number times the same number times the same number. Well, that's 2. This becomes 2. So now it's 2 cubed, which is 8. No big deal, huh? All right, try to do this one on your own. This one's pretty crazy. All right, if you haven't picked up the hint yet, all you have to do is take this number and divide it by that number. This number divided by that number. This number divided by that number. So this becomes 12 divided by 3, which is x to the 4th. 9 divided by 3, which is y to the 3rd power. And then z, take the 3 and put it to the 1st power. So this is my answer. All right, getting the hang of it? All right. Here is the idea of circular motion. And this is the formula for finding the speed when you have a certain amount of pull or acceleration from the object in the middle times the distance that object is from the middle to the object on the outside. So imagine this is an orbit. You've got a planet or a star here, and the orbit here of this planet is moving around. S is the speed or the velocity, d is the distance, the radius of the circle, and p is the acceleration or the pull by that body on the inner side. So what we're going to do now is we're going to find on our own, we're going to find some speeds here. If the distance from the Earth to the Sun is 150 million kilometers and is traveling 30 kilometers per second, what's the polar acceleration from the Sun on the Earth? Go back to that equation we just had. Hopefully you wrote it down. Rewind the video if you didn't. And I want you to plug in these numbers and see what you can come up with. Remember what the radical sign means? It means exponent to the half. I'd like you to write your answer in scientific notation too. It might be really helpful for you to draw a diagram. Here's one if you'd like to use this one. Here's the Sun in the middle. What's the distance to the radius of the Earth's orbit? 150 million. The speed we know is 30 kilometers per second. What's the pull? How much pull does the Sun have on the Earth? Why don't you plug it in the equation and see what you get? All right, here's the equation, and here's kind of what you get. You get the 30. You got to square it because you got a radical over here. Well, how do you get rid of the half? Think about it. This is a half. What's a half times 2? It's 1. So those go away, and then you get 900 divided by 150 million. What'd you get for that? Really, really small number of a pull. Huh. But it's amazing. It makes the Earth go around the Sun. Pretty cool. Now, what about the Earth to the Moon? Well, it's 400,000 kilometers away, and it's traveling 1 kilometer per second. What's the polar acceleration from the Earth on the Moon? Again, write your answer in scientific notation, draw a diagram, plug it in the equation, see what you get. Here's my fancy diagram. Kind of looks like a bowling ball traveling around the Earth. It's screaming, "Oh!" Get it? All right. Here's your equation. We're going to square 1. That's easy. And then remember, this is a half. Well, squaring a half gives you 1. So then we get 1 over 400,000. All right, now, compare the two different poles from the objects at the center of the orbits. What do you see? What do you notice? Would you think one would be bigger, smaller? Surprise you? Pretty cool to think about how we can use math to talk about the planets, huh? Well, that's pretty much it. Can you find a number with a rational exponent? Do you know how to find that? If you don't, definitely go back, rework some of the problems, see if you can get it. But that was really it as we talked about rational exponents. Pretty simple. Hope you enjoyed this lesson. This is Matt with mathsmath.com. Check us out on Facebook at Solving Maths Problems or on Twitter, Maths Math. Enjoy math!